All right, so this morning I already went over some R code with you, so I'm not going to repeat all of that. But just so you know that now that you're in Atlas, you can go to that tab that is the R code and see that there is R code now generated based on the choices that you made in Atlas. So the purpose of that code is to be a starting point. If you just copy-paste that into your own environment, it's probably not even going to work because the cohorts need to be instantiated and you need to specify the connection details and etc. And you may actually want to modify some of the choices that, or further refine the choices that you made in Atlas, like adding custom covariates, even though we may not think that's the best idea in the world. What the R code does is it performs the analysis as specified in Atlas, and it generates diagnostics. So this morning I already disclosed that what I was showing then was actually no longer the code that is being generated by Atlas, because Atlas adds this abstraction layer. So what is that abstraction layer? Well, this is you can think of it as an execution automation layer, in that whereas we previously discussed how to perform one analysis, you might actually want to run multiple analyses. For example, you want to do a main analysis and several sensitivity analyses. You may want to include negative control outcomes. And you may want to not restrict yourself to just one T and one C, but do multiple comparisons all in one go. And actually, the cohort method package allows you to do that in a very efficient manner. So if you have multiple analyses, for example, with different outcomes, the package is intelligent enough to know that it can reuse the same propensity model for all of those. You actually save a lot of compute time, and you can have the package figure that out for you and not have to worry about it yourself. Basically, the idea is that you define a set of TCNOs, and for some reason, for historical reasons, it's sometimes still referred to as a drug comparator outcome pair, but we'll need to fix that at one point. Yeah, I don't know. So you can define multiple of those, and it's actually one T, one C, and multiple O's in one of those sets, as I'll show later on. But you can have multiple TCOs altogether, and then you can have one or more analysis settings. Feed those into the package, and what it will do is it will actually create the full Cartesian product of all of these. So for each and every one of these T's and O's is executed with each and every one of these analysis settings. So if you have 10 on this side and 10 on that side, you get 100 analyses that are being performed for you. Well, no, that is a good point. So at this point, it becomes really easy to do a lot of analysis and produce a lot of estimates. And that is a point where you should really start to worry about multiple testing. Unless the only reason why you're running these many analyses is for example, negative controls, because those are actually not multiple testing, because you're not doing significant testing or anything like that.
But in your outcomes, you have simple ones. If there's like 4 outcomes, you've showed us that you've done an outcome cohort, which is one of those outcomes. Could you do an outcome cohort that has 4 with the 4 outcomes you're actually looking for, and have it only run once instead of run 4 different outcomes?
Yeah, so that's basically a composite outcome or composite endpoint, I think is what you're referring to. And so the way that you can do that, but the way that you currently need to implement that is you need to go to Atlas and basically create the OR in Atlas and create a new cohort definition based off what would be the OR of those things. But you could definitely do that, and we have done that in the past. You could even cheat that and have the 3 cohorts and then write some custom SQL to like take the first of those 3 cohorts and automatically generate that for you. I mean, we've done that because we're lazy. But to answer your question, yes, you can definitely do that. And sometimes it really makes sense to do that, to create a composite endpoint. All right. So let's see how that works. And there's a vignette specifically on this subject of creating multiple analyses, or running multiple analyses at once using the cohort method package, which goes through a full example But just to give you an idea, you need to define this TCNO, which is still called drug comparator outcome in the package. But this funny notation simply means that, so this is what is output by Atlas. It's specifically mentioning that this function is in the cohort method package, just to avoid confusion. So, but don't pay any attention to that. All you're doing is creating an object that defines the T, the C, and the O cohort, and actually you can also specify covariates to concept IDs to exclude and include when you're creating covariates. You can define that at the TCO level, or you can define it at the analysis level, and it depends a little bit on what the thing is that you're excluding, at which level you probably want to define that. But here we choose to define that when we define the TCs and Os. One thing to point out here is that, so these are actually, I'm not actually using numbers here, I'm using variables that were set earlier in the script by Atlas. So a couple of lines back, you'll see target cohort ID is number 1, 2, 3, 4, 5. So that's why you're not seeing the actual numbers here. What you also see is that there is one T, one C, but there are actually now multiple O's. So we have an outcome list, which in this case is just one outcome, which is the upper GI complication that we define. And there is a set of negative controls that we defined. And Patrick didn't have time to go into that, but he actually created a set of negative control outcomes. So these are things that are believed to neither be caused by celecoxib or diclofenac, and that we're using as negative controls. And so what we're saying is that we want to include all of those and basically produce estimates for all of those outcomes. So we create only one TCO object, and we put that in a list, and we'll use that later on. The next part we need to define is the analysis. And so whereas this morning you saw me call the function match on PS to match on propensity scores, because we're automating this, and I can't actually do that because I want the package to do that for me at a future point in time. So I'm not going to call match on PS, but I need to specify which arguments the package will use when it is going to call that function. So we have for every one of those functions that I discussed this morning, we have a function create function name args. So in this case, we have a function create match on PS args, where you can define the arguments that will be used later on to call the match on PS function. I hope that's making sense. So things like the caliper and the caliper scale and the max ratio I'm defining here. I'm not defining here the study population, because of course that's something that will be filled in later on. So I don't need to define that. That's actually for the package to figure that out for me later on. So just need to define the caliper and the max ratio in this case, and that should be fine. I put that into an object that really just holds these variables and doesn't do anything spectacular. And then I create a full analysis by calling create CM analysis, where an analysis gets an ID, which is just a unique identifier. I can give it some description. And then these are all of these objects that I created earlier. And I didn't show all of them, but here is my match on PS argument object that I just created, and I say use that to match on propensity scores, and of course, yes, match on propensity scores. So here I'm saying use these arguments to load the data, use these arguments to create the study population, create a propensity score with these arguments, match on it using these arguments, and fit an outcome model using these arguments. So I've fully specified what I would be calling R with, but I'm not going to do it myself. I'm going to let the code do it for me. Is that still making sense?
Which of these things represent iteration over multiple sets of parameters? Like you just created one propensity score argument set. Is there a way to list them, or are we doing that outside of this?
So that's a good question. So if you actually want to try out different settings, so like if you want to do sensitivity analysis, so this is just one analysis. So I create one of these objects, and then I say, well, maybe next time I want to do another analysis where I don't match, but I want to stratify. I create another analysis object. I give it another analysis ID. I change the description, saying now using stratification or something. And then I say I don't want to match on propensity score, but I want to stratify. And I create another analysis that maybe looks almost exactly the same as this, but has a small change. And I can create like many different analyses. And you may think, well, that's not very efficient, but the package itself will actually be clever enough to figure out, oh, you just changed this bit, and I can reuse, like the propensity score distribution, I don't have to recompute between analysis 1 and 2. If I'm the only difference is I'm going to do matching in one case and stratification in the other one. So actually, it is already intelligent enough to do that. So you just need to create maybe a large set of analysis, but that's fine because it's not going to slow you down.
So we can have a loop and we build a list of like CM analysis list, that is just as one element, we could append it to a list, say.
Yeah, if there are so many analyses that you actually can't be bothered to create them automatically, you can even create in R, of course, just a loop that spins out a lot of these things. And I've seen people do that. They create like, I don't know, 100 analyses because they want to permute over a lot of different things, and then you get into the problem of multiple testing. But yeah, it is certainly possible to do that. But in this case, we just only have this one analysis, but we could easily have many. And then we call this function that's actually going to do the work called the run CM analysis. And so what you need to feed it is, well, first of all, I actually pulled out that code, but you need to specify how to connect to the database, what the schema is for your CDM, where the cohorts live. You need to have an output folder, so something on the local file system where all the end result files and all the intermediate files are all going to be saved. So that's something you need to specify. Then here are the two things we just talked about, the list of analysis and the list of TCOs. And then there's here this block that is just telling you whether you want to do some things in parallel. Like if you, in this case, we have, I don't know how many, 50 outcome models because we added 49 negative controls. We could have the computer do them in sequence, but if I have 4 cores in my laptop, for example, I could do 4 in parallel, and I'd probably be almost 4 times as fast. And the same goes for all of these other things that if you have more cores available, it's probably going to need to have use them.
You mentioned earlier that with multi-testing, you expanded the confidence intervals. When you're doing all these together, does it know whether it's negative control, which means it doesn't need to, or if it's not negative?
So this isn't doing any adjustment for multiple testing. You have to do that yourself later on if appropriate. All right, so first of all, obviously this, if the separate components can take a long time, this function can take an even longer time to complete. Because it actually is calling the getDB thing, and it is fitting the model, and you might want to do hundreds of them. But again, that's such compute time, so probably don't want to do it on your laptop yet.
So I was going to ask, because I've been trying to do this simultaneously, but like bastardize it to how I wouldn't use Atlas, I would go to where I actually call. Would you say that as a community we have help or support to help us make sure we construct our exposure tables and outcome tables kind of in similar, like to make sure it's really a one-to-one and we're switching out like pieces we're explicitly pointing to somewhere else? Like, have you guys kind of helped people hack it together to their native stack? Or would you help someone who's trying to maybe do it both in Atlas and then show people if they don't feel comfortable using Atlas how they could do it themselves?
Right, with the table structure.
Yeah, like making sure the tables are really comparable when you're explicit.
I think the documentation, you mentioned that before about table.
I see parts of it, but there's like making sure the structures are one-to-one seems to be a little bit of an implicit reference.
That would be very helpful.
Yeah, I don't know if other people have that.
So are you talking about specifically the structure of the cohort table?
Like, yeah, when we're really directed to these explicit things, most of them I can figure out from your documentation what they are, but there are a couple ones where I'm just not sure my version and your version are the same thing. I just can't, I haven't been able to rectify it. It sounds like maybe other people have.
But by thing, do you mean cohort definition?
Like, yeah, so for an exposure table, let's say I've staged an exposure table the same way I would in my, not necessarily using Atlas, but using the same approach, but I just want to make sure it's exactly the same thing when I plug it in. And ours like not happy at me because I'm giving it something that's just a little bit not what it expects.
So it's very explicitly, it's the cohort table specification. Like in the CDM, there's a table called cohort. That
So we
cohort,
should just map the structure to the, so
the,
if
yeah.
it maps to that, okay.
So the cohort definition, the cohort table in the
Yeah.
CDM, that is the proper specification for a cohort.
Okay.
Whether you instantiate that cohort table in any schema or
Yeah.
give it a different name, but that's the structure. That has to be the
That's
four
structure.
fields.
Yeah,
Okay.
yeah. Good, yeah, good point.
Yeah, I don't know what I was thinking it was like.
Well, so that's a good point. So which version of the CDM are we talking about here? So generically, we talk about version 4 and version 5 because most of the time we're actually not using stuff that is specific to version 5.1 or 5.2. So like whether or not there is a date time field doesn't matter for the cohort method package because it actually completely ignores it. It's as simple as that. The package isn't built to deal with time, it just deals with dates. And well, maybe in the future code, so you can specify which CDM version it is, which currently has option 4 and 5, but Atlas doesn't work on 4, so you're probably in trouble anyway if you have 4, but Marc.
Do the comparisons have to be made of the cohorts from the same data sets, or is there a way to somehow to compare results from, let's say, PCR, CCAE data set? The different results will be, but is there a way to?
No, so they have to. So even though the exposure cohorts and the outcome cohorts can be in different tables, they all have to be derived off of the same CDM instance because you're going to be creating, for instance, you're going to look at the CDM to create the baseline covariates, and then like if the person ID doesn't match, then you're going to do very wrong things. Yeah, it all has to be within the same instance. Yeah, we don't have a way of comparing across CDM instances or doing analysis. Maybe one more thing that is nice to mention is that, so I said this might actually take a long time to execute, but what it will do is it will, as soon as it's finished something, it will write it to this output folder. And if for some reason, I don't know, your computer crashes or whatever, you need to restart, it will first look to see whether that specific artifact that it needs to create already exists, and if so, we'll skip that. So it will download all of the data from the database and write it to a cohort method data object, and then next we'll do fitting of propensity scores. If at that point in time you say stop, and then the next day you come back and you say start, it will automatically skip to fitting the propensity models. So that is a neat feature because it can be a long time to run. All right, so what is this result object that comes out of it? Well, you might be disappointed to hear that it's not containing the results. It is basically a reference object that tells you where the results now are. So for every TCO analysis combination, which can be many or can be few, it gives you the path to the cohort method data file, the study population file, the propensity score file, the match population file, and the outcome model file. So you can just load those and do anything with them that you want to, like load the outcome model and look at the estimate that came out of it, or you can load the propensity score file and plot its distribution, for example, if you want to. If for some reason you lost that object before you saved it, actually it already is automatically saved under the name outcome model reference.rds in your output folder, which sometimes might be interesting to know. What you probably want to do is you want to call this function called summarize analysis, which takes as input this results object, and it creates the analysis summary, and that contains for every TCO analysis ID combination things like the hazard ratio with its 95% confidence interval, the number of people that are in T and C after matching and trimming and whatever, and the number of subjects in T and C that have the outcome O. So things like that you probably want to report in your paper. So the code that Atlas generates actually then goes further, and it also generates a bunch of diagnostics and puts those also into the output folder. So one diagnostic that it creates is the attrition diagram. So in this case, I ran the garbage study on one of our databases, and we see that we don't actually have that many people to begin with. And in the end, we have even less people to, to fit the model. In this case, 1,852. So that is maybe something to worry about. But we're not going to do that right now. We also can find the propensity score distribution plots in the output folder. So even though these drugs, we discussed it, it's probably given to very different types of people. There's still some overlap between the two groups, so it's not all bad. And after matching, we see that actually the distributions, of course, is forced to basically be this purple bit here that we see here. Yep.
If there are arbitrary criteria how much overlap is great enough for an analysis, what do you say?
Yeah.
What should you say if this two group of people are too different and I should not move forward?
Yeah, so that's a very good question. So when is the overlap too small to be considered good? And so there aren't any hard and fast criteria except for one. Proposed by the same person that proposed the preference score distribution, Alec Walker. He said that, Patrick, remind me, was it over half should be within?
Half of the target, greater than 50% of the target and greater than 50% of the comparator should be near clinical equipoise, defined as between 0.3 and 0.7 on the preference score.
Yeah, so half of each group should be within, let's say, these two bounds here. Then that's what he would consider a good overlap. But that's pretty strict. I think we actually fill that pretty often.
Oh, after matching.
No.
They failed it actually that much.
Okay.
It's not a hard and fast rule like you should definitely stop, but if you do see that you have less than that, you should at least take pause to think about, is that comparison clinically meaningful? Because what that rule is basically saying is, there's a majority of the people who look like they were approximately equally likely to get either drug. So they were just like you guys with the red and the blue pill. If you actually have a majority of the people outside of that space, it's people who look inclined to have been red people or looked inclined to be blue people. And you can perform an analysis, but you have to think really carefully about what question are you answering at that point.
Yeah, so just to give an example, so extreme, this is good. So actually, almost everybody is in what Alec would have defined as the clinical equipoise area. This is an example that is bad, because almost everybody is outside of that area. Most of the people that got the red drug would never have gotten the blue drug and the other way around. So yeah, as Patrick said, if you're going to do a comparison here, you can get it to run, because it will actually create a matched set, and it's going to be a much smaller set of people. And there's also, but then the question is, well, who are these people that for some reason are still comparable? Because you'll get people like these that are, well, anyway, so a lot of people are going to be matched to people that are quite the opposite of what they were expected, or getting quite the opposite of what they were expected to get.
This might be a reasonable place to ask the question. One of the options that you guys have encoded here was how to restrict your cohorts based on that distribution, for instance, score distribution. And one of the options there was by equipoise.
Yes.
By percentile.
So given that these are the distributions that you observe, you have quite a number of things you can do. So you can choose to match, so you can go to this. You can choose to stratify. You can also choose to trim, and there are multiple ways to trim. And so one is, the most often thing to do is you just trim a certain number, a percentile of people that are at the extreme. So 5% of the blue people that are at this side, and 5% of the red people that are at that side that you throw away, things like that. Another option, based again on what Alec Walker is throw away people that are outside of this range of the preference score. So for example, throw away everybody that has a preference score lower than 0.25 or higher than 0.75, which I think is actually the default settings for those, for that specific function. So you can call that function instead of, or maybe in addition to doing the matching or stratification or.
Oh, in addition to, so typically it would be in addition to them. I can't imagine that figure would look so much less impressive. It's just truncated on two sides. You still have these non-overlapping areas, with substantial kind of mass in the distribution.
Yeah. So what typically is done is you do so. The trimming by equipoise by those ranges that I just said is pretty drastic anyway, so you don't actually see that often. You typically see the 5% being removed, and then in combination with either stratification, matching, or inverse probability weighting. And so currently we are working on adding inverse probability weighting. So those are the combinations that you typically see. But just trimming in itself is not something you see done very often.
If this plot and one the feature flow prior to this line is automatically output from the script, or we have to run some code to get this.
So this is automatically generated. So you just find the image files in the folder. But you also have the R code that shows you how it was generated if you want to know how to.
Two questions. If you see those like two propensity score distributions that are very separate, can you go back to your cohort definition? Because it could be that you're missing like an indication. There could be an indication that's separating out those patients. Like, could this be a diagnostic maybe that you did?
Yep. So that's a very good point. So one question is, if you see this, what do you do then? And one response could be, oh, we can say we need to stop. We can't do this comparison. Another thing could be, like you said, we maybe need to rephrase the question. Maybe overall these two drugs are incomparable, but maybe if we focus on a specific indication. So we're talking about celecoxib and diclofenac. Maybe if we focus on back pain as an indication and nest our entire study in that group, maybe then it will be a better comparison. And that's totally fair game, yeah. That is probably a good solution to this problem.
And then the other question is, so trimming with matching. I mean, when you're matching, you're already losing quite a few people. And then if you start trimming, you're losing a lot more people, and you're getting this really unique, small subset. Like, is it even worth it to trim after you've matched?
Yeah, good question. I really don't know the answer to that one. For some reason, I don't use trimming that much. If you do inverse probability weighting, you probably will have to do it. And yeah, it's a bit of a question how much power is left, and also how much residual bias do you have. And so one of the next slides will actually try and address that.
Yes, in addition to power and residual bias, how much generalizability to the population?
Yes, yeah.
So and since that's, you've got data to produce metrics on that, and some even more brilliant iteration we have to run.
Oh, we have been thinking about that. How do you show generalizability? You can actually just, like currently, like we're comparing the T and the C, you can compare the population that you have at the end of all of your restrictions to what you started out with and just see how. Yep. Yeah, so yeah, we should probably do that. Yeah, good idea. All right, so another diagnostic automatically generated is this plot I already showed. So this is the standardized difference of mean of all of the covariates that were included in the model. So every dot is a covariate, and on the x-axis is the standardized difference before matching, and here it's after matching. And so the usual rule of thumb, everything below 0.1 we consider to be balanced. And in this case, we see that we are actually balanced on all the covariates that we had in the model. If you see that there are a lot of things that are out of balance, then again, you need to worry about what's going on here, and maybe I should stop this analysis before I go any further and make wrong inferences, because there is a large chance then that you'll actually be confounded in your results. Another way to visualize this exact same data is this plot. That's also automatically generated. And I know you can't read it, but let me explain what it is. So on the x-axis here is the standardized difference of mean, but in this case, the previous plot I was using the absolute value. Here I'm using actually, so this is positive, this is negative, so anything here means that the difference is 0. The red dots is where you started before matching, and then the blue triangles is where you ended up after matching. And these two trellises are basically showing you the same data, but ordered in a different way and just taking the top. So the top one is ordered by what has the largest difference before matching, and the bottom one is showing you those same things, but then ordered by what has the biggest difference after matching. And so even though you can't read it from in the back, you see here that age group 15 to 19 years old was the biggest difference before matching. So I think this means that the diclofenac users were much more likely to be 15 to 19-year-olds than celecoxib users, which makes good sense. And after matching, that's actually the difference was completely eliminated. If we want to see, well, how bad does the situation look after matching, you see that actually the biggest difference is iron deficiency anemia in, I can't even read it, well, in the year prior. So that there was a difference before matching, and that actually hasn't changed. But it's a very small difference. It's smaller than 0.1, as we already saw in the previous plot. So if you want to know what the specific covariates are that are out of balance in this plot, it's a good one to look at.
Maybe I cannot see very clear here. What was the difference between left and right panel? Minus.
But yeah, so this is it's on an absolute scale. It's not on the previous one was on an absolute scale. So if something couldn't be negative, but here the differences actually can be negative and positive.
Say the top one, the age group 15 to 9.
Yes.
There's a rest dot on the left.
Yeah, so it's strongly negative. So that means that it was actually in the target group, it was much lower than in the comparator group. So if the target group is celecoxib, it actually means that there were far fewer people in this age group in the celecoxib group than there were in the diclofenac group, which makes sense because you normally wouldn't prescribe celecoxib just like that to a young person. All right. So the last diagnostic that is generated is maybe a little bit hard to explain for the people that haven't seen this plot before, but those of you who are on a lot of the calls will recognize this plot. So what this plot is showing you on the x-axis is the relative risk. And we're doing a Poisson regression, so in this case it's a incidence rate ratio. On the y-axis is the standard error, basically the width of the confidence interval. So the higher you go, the wider your confidence interval is. This yellow diamond is your actual estimate for your outcome of interest, the upper GI complication. And all of these blue dots are all negative control outcomes. So there are other outcomes, things not upper GI complications, that we've selected previously, but we didn't show it, that we believe is neither caused by celecoxib nor diclofenac. But even though they're not caused by those drugs, and they could be confounded in a way. And if you don't adjust for confounding, you would imagine that they can actually have very large effect sizes, even though there is no real effect. And so we use those negative controls to check whether we actually have good control for confounding. And so what you hope is that all of these blue dots are above this dashed line that indicates the statistical significance boundary. So anything below this line is statistically significant at 0.05, and everything above it is not statistically significant. And so the good thing that we see here is that all of these negative controls that we included are not statistically significant at alpha 0.05. So the negative controls are all negative, so they do give us a good sense that we don't have a lot of residual bias in our study. And this should include unmeasured confounding, so that's pretty neat. We also add this orange area. This is a little bit more complicated to explain. Given the distribution of estimates that we observe for these negative controls, we actually fit an empirical null distribution. And based on that, we can actually fit create a calibrated p-value. And this is the statistical significance boundary for the calibrated p-value. Basically, what it does is it tries to see whether the variations that we see for the blue dots is completely explained by the standard error that we have, so the random error. And in this case, because these lines are not exactly the same as the nominal statistical significant boundary, we can see that there is actually a little bit more variance in these estimates than is explained just by the random error. So even though all of these dots are above the dashed lines, there does seem to be some evidence that there actually is some residual confounding. But we have a bit of a problem in that we do not have a lot of power for these negative controls, so we're not exactly sure. But anyway, overall, we should feel good about this plot that is showing that there's not much, or at least none of our negative controls are statistically significant, which is actually more than we would have expected. Does that make sense? All right. And with that, I am at the end of my talk. What's next up? All right.
Sir, can you refresh my memory? Where did you specify the negative controls again?
So there is an option in Atlas to actually pick a set of concepts to use as negative controls. But yes, yeah, you need to pick your negative controls completely manually. There's no, we have a semi-automated process where, based on the Larity's knowledge base, you can actually generate a candidate set of negative controls. So things that, so we, of course, in Larity's you have the product labels, you have basically a PubMed analysis, and you have spontaneous reporting data. And so if something based on those three things appears to not be related to the exposures, it is a candidate negative control, but you still need to manually review it.